The biggest question is actually the practice exam. The midterm exam should be listed as due November 8th in both places. The course manager had originally set up the practice exam to be due November 1st to make sure people had it done completely before they started the actual exam. I decided to go in and extend that in WebAssign so that you guys could practice and view that exam up until you take the actual midterm. So I extended it till the 7th in WebAssign. So that is fine if you take up until the 7th to complete the midterm practice. That is okay. Okay, so this week's topic. We're looking at estimates of population characteristics. Now, most textbooks call these population parameters. One way to estimate them is something called a point estimate. A point estimate is a single number based on a sample that represents a plausible value excuse me, for that population characteristic. So let's say that the school wants an estimate of what the average amount students spend each semester on textbooks. So they are going to take a simple random sample of 300 students, gives a mean of $582 spent on textbooks. So they would, their point estimate students spend around $582 per semester on books. So we just use that sample statistic to estimate that population characteristic. Now remember we talked about that central limit theorem. For distribution of sampling distributions, where we found that if our population is approximately normally distributed, if we take all possible samples of size n, then we take the mean of those samples or the proportion of those samples. Those sample means are normally distributed and they're centered at the population mean. Of course, the spread is smaller. The spread is adjusted. The standard deviation becomes a standard error which is equal to that standard deviation divided by the square root of that sample size n. So you can see that the spread is reduced. It's a much narrower curve than just the distribution of the individual values in the population. An unbiased statistic is a statistic that is whose sampling distribution is centered around the population characteristic. Again, whether that's the mean or a proportion. Well, because these point estimates leave a lot of leeway there, I mean, it could be our point estimate could be dead on. It could be right in the middle here. But we could have had a sample that had a mean that was way smaller or a mean that was way larger. So it's not guaranteed. It's more likely to be towards the middle, but it's not guaranteed to be dead on or even extremely close. So what we do is we use something called an interval estimate. For an interval estimate, we're looking at an interval, again, derived from a sample of plausible values for the population characteristic. Now, the most common type of interval estimate is a confidence interval. And that's what we're going to be using in this class. So in a confidence interval, we have a chosen, pre-chosen degree of confidence. That the actual population value will be in that interval. This degree of confidence is from, for confidence intervals here, from either a normal distribution or from a t-distribution. Well, let's look at what is a confidence interval? How does it work? Well, let's go back to that sampling distribution again. We know that if we keep taking samples, again, if this is the population, the samples are going to have means that are distributed around that population mean. And of course, their distribution is going to be a little bit narrower than the population distribution. Something like that. That was really sloppy, but you get the idea. But we know they're going to be still spread out. They're not going to be dead on the center, not dead on the mean of that population. We see that they're going to be spread out. But from our central limit theorem and our sampling distributions and probabilities from last week, we know exactly what percent should be within a certain range of those sample means, should be within a certain range of that population mean. So we decide on that percent, that's our confidence level. 95% would be a 95% confidence level. That would mean that 95% of the samples would produce means that are within that distance of that population mean. Excuse me. Well, the thing is, we don't know what that population mean is, but we do know we are able to calculate that distance even without the population mean. So what we do is we work backwards. We have that distance. We just take a sample and we take the sample mean. Let's say our first sample mean is right here. Well, so it's right there. We go that distance, so that far to that side. That far to that side, we see it does contain, it gives us an interval that contains the true population mean. Maybe our second sample gives us a mean like that. We go to that side and that side. Again, we see that that interval contains the true population mean. Maybe our next sample gives us a mean right here. We go out. Again, that contains that true population mean. Will all of them contain that? No. 95% of them will contain it. So that means 5% will not. This one here, you can see, just misses the true population mean. Now, even the ones that miss will be really close. So those are the confidence intervals. Well, the key term here, of course, that center dot, the dark dot, is just the point estimate. That distance going out here is called the bound on the error. The bound on the error is calculated as a critical value times the standard error of the means. Or the standard error of the proportions, depending on which population parameters or characteristics we're trying to estimate. So let's take a look. We're going to do population proportions first. Now, confidence intervals for population proportions always use the normal distribution. In other words, they're Z intervals. The bound on the error is going to be then that Z critical times, if you recall what the standard error is for a proportion, it's the square root of P times 1 minus P divided by N. Now, we're not necessarily going to calculate that by hand. We're going to let the calculator handle this for us. But there are some requirements that we have to be aware of. First, N times P has to be greater than 10, and N times 1 minus P has to be greater than 10. Technically greater than or equal to 10. Second, N has to be less than 10% of capital N. In other words, the sample size has to be less than 10% of the population. And the sample is randomly selected from the population of interest. Which that one kind of makes common sense that it has to come from the population of interest. So our example here. A random sample of 240 students gives 187 past statistics on their first try. Create the, let's go 90% confidence interval for the population proportion. Well, first of all, what does that 90% mean? That 90% is what determines our critical value. The Z critical comes from the 90%. So let's look at that first. This goes back a couple of weeks where we had 90% out of the middle. That's what that 90% means. We're taking 90% out of the middle of the curve, which means there's 10% outside of that. Well, that 10% is split evenly, 5% to each side. Well, that makes this the 0.05 cutoff. And this up here, the 0.95 cutoff. So we can find those critical values off of that. So off to the calculator here. Oops, I don't have my calculator up. Excuse me. There's my calculator. So second distribution, inverse normal. 0.05 is one that we're looking at. This is a standard normal distribution. We're looking at z-scores, in other words. So it's a mean of 0, standard deviation of 1. We get a negative 1.645 for that one. Let's look at the other side. So 0.95. We'll notice we get the exact same number, it's just positive. Well, we use the positive one is our critical value in the calculations. So that's telling us that 1.645 would be that Z critical. Now, we don't necessarily need that here because we're going to go back to the calculator to find the confidence interval. We're going to go to stat, tests. Now, these are all tests up here. Those are hypothesis testing for next week. Number 7 here is a Z interval. Now, what we're looking for here is a Z interval, but that's not the one we want. There's a special one for proportions. There it is, option A, 1 proportion Z interval. Now, it looks like my information's already in there. We have 187 is X. That's the number that have the desired property. That's how many passed on the first try. Out of 240. Confidence level is 90%. So we got to change that to 0.90. And calculate. And there we get that interval, 0.73512 to 0.82321. So our conclusion, the proper way to state it is we are 90% confident that the true population proportion is between 0.73512 and 0.82321. Now, some might say, well, that would that be the same as saying there's 90% chance that the true proportion is in there? That is not true. That's not the way this works. 90% is not a probability. It's a level of confidence, and it's a very subtle difference, but it's not saying there's a 90% chance that it's in that interval. It's saying that if we repeated this process over and over again, 90% of the intervals we created would contain the true population proportion. Sorry. Okay, so the next thing I want to talk about is something called required sample size. This is the main reason I put that bound on the error formula up there earlier, because we're going to solve that bound on the error formula for n. If I rearrange it, it becomes this: n equals p times 1 minus p times our z critical divided by the bound on our error, where that combination of z critical and the bound are squared. So what this gives us is, if we were hoping to keep our bound on the error within a certain value, it tells us what is the minimum sample size that we would have to take to reasonably expect to be within that bound of the error. So let's take a look at an example here. Find the, come on. Excuse me. Minimum sample size required for the bound on the error of a 95% confidence interval for a population proportion to be within 0.03. Now I need a little bit more information. If we have an estimate of p equals 0.35. We'll see in a minute why that estimate is important. So this is saying our sample size n equals 0.35 times 1 minus 0.35 times 95% confidence interval, or z critical is 1.96. I'm just going to give that to you for now. Divided by b of 0.03, that's going to be squared. So let's do this in the calculator. So 0.35 times 1 minus 0.35 times 1.96 divided by 0.03 x squared. We get, something went wrong there. Let me clear that out. Oops, I see what happened. 0.35 times 1 minus 0.35 times 1.96 divided by 0.03, close parentheses, and squared. We get 971.07. Now that is the minimum size. So even though it's only 0.07, we round up, always round up. So we're going to use a sample size of n equals 972 as the smallest sample size that we could take to reasonably expect that bound on the error to be within 0.03. Well, that was if we had this estimate of P. What if we don't have an estimate of P? Well, then we use P equals 0.5. The reason being is if P is 0.5, that's the worst case scenario. It gives us the largest possible sample size. So all that does is it changes this whole formula up here. We take out the 0.35 and put in 0.5. Let's calculate that out and see what happens. So we've got 0.5 times, now 1 minus 0.5 is just 0.5 again, so I'm just going to enter that. What's in this parentheses doesn't change, 1.96 divided by 0.03. Then it's still squared. You get 1,067.11. Well, again, because that is a minimum size, we always round up. So our minimum required sample size is 1,068. Notice that's considerably larger than what we had before. That's because when we put in the 0.5 for P instead of 0.35, it forces us to go a little larger. It's a worst case scenario. So this might be bigger than what we need, but we'd rather be too large than too small. Now let's talk about confidence intervals for population means. These are going to be broken down into two categories. One, we know the population standard deviation. In that case, it's going to be a Z interval. Two, we do not know the population standard deviation. In this case, it would be a T interval. Though the T distribution is a lot like the normal distribution. It is bell-shaped and centered at 0. However, the normal distribution is determined by a mean and standard deviation. The T distribution is not. There is no mean other than 0 for a T distribution. What varies from one version of the T distribution is the degrees of freedom. Degrees of freedom here on known as DOF. A degree of freedom is ability to vary what it is. What it really comes down to, degrees of freedom in this case is just the sample size minus 1. The t-distribution is always more spread out than the normal distribution. And as degrees of freedom get large, it is approximately the normal distribution. In fact, a lot of textbooks only go up to a certain size for the t-distribution because after that it's so close to the normal distribution it isn't worth the difference. Well, let's take a look at some examples here. Construct the 98% confidence interval for the population mean if a sample of 53 items gives a mean of 28 and the population standard deviation is known to be 7. So the key phrase is right there. We know the population standard deviation. Since we know that, this is going to be a Z interval. So let's go to the calculator and see what we find. So stat, tests. Option number 7 down here is a Z interval. We have options up here of data or statistics. Data would be, we would have the raw data of our sample in a list in the calculator, and then we'd want the calculator to analyze that raw list of data. We don't have that here. We just have the summary statistics from the sample. So we're going to stick with statistics as our option there. This is our population standard deviation. We said that's known to be 7, so that's correct. X bar is our sample mean, that's 28. N is our sample size, there's 53 items. Confidence level, 98%, so 0.98 we put in there. And we hit calculate, we get 25.763 to 30.237. So we are 98% confident that the true population mean is in the interval or between the numbers, however you want to word it, 25.763 and 30.237. There's our interval. Well, let's take a look at an example where we don't know the population standard deviation. Find the 92% confidence interval for the population mean if a random sample of 42 items gives a mean of 83 and standard deviation of 12. Notice I'm given a standard deviation of 12, but that is from our sample. So this is going to be a t-distribution, or t-interval. So let's go to the calculator. So stat, tests. You got to arrow down here a ways. So it's actually option 8 there, the t-interval. It's still going to be statistics. We're using summary statistics. Our sample mean is 83. Sample standard deviation is 12. Sample size is 42. Confidence level is 92%, so 0.92. Giving us 79.676 to 86.324. So we are 92% confident that the true population mean is between 79.676 and 86.324. Those are all of the different interval estimates for a single population that we're going to be doing this week. Now, similar to the population proportion, there is a required sample size calculation. For required sample size, we must have the population standard deviation, or an estimate of it at least to use. So let's take a look here. Let's say that we have find the minimum sample size required to produce a sample with a bound on the error of no more than 4 if the population standard deviation is known to be 9, and we are using a, well, let's just go with a 95% interval. So a 95% interval gives us a z-critical of 1.96 again. So n equals, now this time the formula is all of this and together is z-critical times the standard deviation divided by that bound on the error, and then it's all squared. So for this set of information, that's 1.96 times that standard deviation of 9 divided by our desired bound of 4. That's going to be squared. It's actually not going to come out to be a very big number, is it? Let's take a look. So we've got 1.96 times 9 divided by 4 squared. It's not, it's just 19.44. Now you notice I was a little sloppy with the rounding there because it doesn't really matter, because we are going to round up anyway N equals 20 is our minimum sample size. Okay, let's take a look at our MiniTab functions for the night. MiniTab, actually, the same function that's going to do our confidence intervals is also going to do our hypothesis testing next week. So I'm going to copy in a set of numerical data here. This is scores on an assignment. You go to stats, then basic statistics. And then depending on whether we know the population standard deviation, we would pick one sample Z. Or if we do not know the population standard deviation, we would pick one sample T. Let's assume that we know the population standard deviation is 8. So we're going to pick one sample Z. Now, the first thing it's going to do is ask us for our known standard deviation. I'll put 8 in there. And it's going to ask us to enter the column of scores, so I can put those in. If we were performing a hypothesis test, we would check that box. For right now, we're not doing that, so we're going to leave it. Click Options. This is where we set our confidence level. We're going to leave it at 95%. Now, if we're hypothesis testing, we would adjust this. But for a confidence interval, it's always that middle option, the not equal to. So we hit OK there and OK again. And we get that confidence interval, 74.20 to 79.74. Now let's do stat, basic statistics. Let's do the one sample T. Now notice it does not ask me for the known standard deviation anymore. Check my options. I do have 95% and it's the not equal to. And you'll see that gives me a little bit wider. Instead of 74.2, it's 72.87 as the lower end of my confidence interval. So that is numerical confidence intervals for a population mean. If I want to find confidence interval for a population proportion. So here's a list of pass or not pass on an assignment. We're going to go to stat, basic statistics, and one proportion. I'm just going to select pass. Again, I should go to options, make sure it's 95%. I'm going to do a 95% interval again. And that's not equal to again there. And there is my confidence interval. And that is really it for MiniTab for this week. Well, I realize I really flew through that tonight, but it is time for the meat quiz. I'll give you guys a couple minutes to work on those problems, and then we'll go through them. So for number one, create the 96% confidence interval for the population mean if a sample of 70 items gives a sample mean of 18 and a standard deviation of 4. This is saying the sample gives a mean of 18 and a standard deviation of 4, which means that that standard deviation is for the sample. So we're going to be using a t interval. So we're stat, tests. Option 8 is t interval. Our sample mean is 18. Sample standard deviation is 4. Sample size is 70. Confidence level is 96%, so 0.96. Which is 16.999 to 19.001. Now for number 2, how large of a sample would be required to reasonably expect the sample mean to be within 1 of the population mean? In other words, the bound on the error to be within 1 at 96% confidence if the population standard deviation is known to be 4. So we do know the population standard deviation there. We do have to find that critical value. This is 96%. So it's 96% out of the middle, which means it's 2% to either side. So it's 0.98 that we're looking at there. So second distribution, inverse normal, 0.98. Remember, it's 0.02 and 0.98, but 0.98 will give us the positive value. 2.054. So that is our Z critical. So it's 2.054 times that standard deviation of 4 divided by standard error of 1. And I'm just going to do that off camera. Giving me 67.5. So N equals a minimum of 68 is our minimum sample size. Well, that's about all I've got in me for the night, folks. I realize that was a little bit of a short one. I apologize for that. Hopefully you got everything you needed for the work for the week. Make sure you are ready for the midterm and get that done. There can be no extensions on the midterm. So make sure you've got your Proctor arrangement set up. If you're using ProctorU, make sure you've tested your computer. Make sure your computer is compatible with ProctorU software. Other than that, if you need anything, please let me know. Otherwise, you have a great week and hopefully see you next Tuesday.